Welcome everybody to this week's Ask an Astronomer episode. I'm Stefan, I'm a PhD student at the Institute of Astronomy, and today with me I have Stephen. Do you want to introduce yourself a bit and say a bit what kind of the field you're working on?
Yeah, so hi guys, I'm Steve. I'm also a first year at the Institute of Astronomy, and I work in the area of planetary system evolution. So planetary systems are systems of planets. So we have our own solar system. We have the planets, and they go around the sun. And there's comets and asteroids and other small bodies, and these also occur around other stars. And mostly they all just go, the planets and the comets and the asteroids go around the star, but there are massive planets that can affect things in there. Like Jupiter can really affect things in our own solar system. It can eject comets into interstellar space, or it can scatter them in towards the small planets. And basically my area looks to say, well, what can planets do to other bodies, and when we look at other systems around other stars, and we see weird things, can we explain that with the effect of the gravity of planets and things like that?
Okay, yeah, probably people heard of this comet Oumuamua, I think it was called, which was, oh, I'm not sure if it was a comet asteroid, I'm not sure of the terminology, but I think it also came from other solar system, so that's probably, well, that might be something that was kicked out by some planet in that system.
Yeah, absolutely. Yeah, could well have been ejected by a planet around another star, and then it went into interstellar space and it wandered over to our solar system. Although I don't think people quite know why it's so cigar shaped.
Ah, yes, right.
That's still a mystery, I think.
Okay, we got a few questions already in advance to this episode. So we got one question on Slido. If there are any simple astronomy experiments that you can do at home. Do you know any nice experiments?
Yeah. So there are a few you can do, and these few they're quite nice because you don't need a telescope to do them. Telescopes are upsettingly expensive, so there's kind of a few you can do without having to buy one of those. So one of those is kind of this is quite a simple one that we did at the open day at the Institute of Astronomy last year, where you get a sort of a white. Well, you can have a container. You put a white substance in it, so flour, say, and then you want a dark powder on top, so you could use cocoa powder. Give it a nice sort of even smattering, cover the white flour, and then you can drop something like a pebble in there. You can throw it in, and that sort of simulates impact craters on the moon. So on the moon, you have impacts from small bodies, comets or asteroids that may have hit the moon, and some are long and streaky, and some are very small and circular. And so you can sort of throw things into into this mixture you've generated, and then you can see the impact crater because the brown cocoa powder will get thrown off, and you're left with this white flour underneath. And you can see a nice little impact crater, and you can throw it in at different angles and see all the streaks coming off, and it's quite a good experiment actually.
This sounds
Um,
like a lot of fun. We should definitely do this, like on stream at some point when we're like back in the
yes,
institute.
very very messy though. So, obviously, yes. Do be careful when doing it. Um, Another one is you can make a pinhole camera. So you get a sort of a small box, so a shoebox would work perfectly. Cut a hole out of it on the side, a 2 by 2 centimeter hole, and put some aluminium sellotape, some aluminium foil over that hole that you've just cut out, and then poke a tiny little hole in it with a pin. So you now have a pinhole camera, and then inside the shoebox, opposite the aluminium foil, you put like a bit of white paper. So now if you direct that at the sun's light will sort of go through that little pinhole you've created, and it will form an image on the white paper, and you can see the sun on that white paper. And basically, if you measure the size of that image and the length of the box, and then you divide the size of the image by the length of the box, and then multiply by the distance to the sun, which is 150 million kilometers, basically, then you get you can physically measure with this pinhole camera the diameter of the sun, so how big it is from from side to side in kilometers. And you can do it with the moon as well, except you have to use the distance to the moon, which is 385,000 kilometers, sort of.
I'm very impressed you learned all those distances by heart. That's very nice. Yeah, that's cool. Like I thought, oh yeah, pinhole camera, that's a cool thing, but pinhole camera to make a picture of the sun, that's really cool because remember, don't look at the sun directly; it's really bad for your eyes.
Yes,
but with this pinhole camera, let's say, it's apparently it should be safe and nice. Can you see like features of the sun there? Never tried it.
I don't know. I think it depends what sort of magnification you're going to get. I mean, the bigger the picture of the sun, the more likely you are to see something. So, I mean, it's not a pinhole camera, so I don't know how different this would be. But I remember the transit of Mercury recently, when Mercury went in front of the sun. Do you remember in the observatory?
Right, we had a big paper behind the telescope where you could see the sun, the image of the sun with a planet in front. Well, yeah, really tiny dot.
Yeah. But I think in a pinhole camera made in a shoebox, that might be something like that would be too small to see. I don't know.
Actually, before you continue, I totally forgot to explain the thing. So I'm getting out of practice. Yeah, so we are here for like 1 hour or so, answering all your questions you have about science, about astronomy in particular, or about how it is to do a PhD in astronomy, things like that. And just write them in the YouTube chat, or if you prefer not to use YouTube, you can put them on the Slido. There's a link you see once in a while up there. And otherwise it's sli.do/ with the number 74747. I really should pick a better number one day. Okay, that's it. And we already got our first question. Okay, why is the exploration of these outer planets important? Are there any efforts going on?
So, not that I mean, there certainly isn't anything sort of going on right now, and the Uranus and Neptune, I think, have been sort of understudied compared to some of the other planets. But I mean, Uranus, for example, is quite fascinating because its obliquity is 90 degrees. That basically means, most of the planets, when they orbit the sun, they spin about their axis, and that's kind of roughly, here's the sun and here's your planet spinning around its axis, whereas Uranus is kind of like on its side, like that. It spins on its side, so it's you kind of think of maybe its south pole is always facing the sun. Think of it like that.
That's interesting.
Which is bizarre. It's quite hard to form a planet that way. That goes against a lot of what we think. So, for example, some people think that might have been formed by an impact. So another smaller planet maybe, or something like that, hit Uranus and caused it to sort of flip onto it, or sort of fall over onto its side, if you kind of think of it like that. And so that's quite important. I'm not entirely sure what we still need to know about Neptune. I mean, Neptune is an important planet. It scatters objects in from the Kuiper belt. That's like a big belt of objects just outside of Neptune, and it can scatter some of those inwards. But I'm not entirely sure what we still need to know about Neptune. That's an interesting question.
Okay, we got actually another question from YouTube right now. Is it easier to study protoplanetary disks that we view from the side, or the ones that we view from the top?
Wow, that's an interesting question. Protoplanetary disks aren't my area, but I mean, if you study them face on, so that's when we look at them, we see this big circle around the star, and when we look at them edge on, we're just seeing that the sort of edge of, think of the edge of your dinner plate or something like that, just a tiny thin ridge. So I mean, if you're studying them face on, then you can see in this nice lovely slide in the background that you can see all the nice gaps that have been carved by planets, or the effects of planets, and you can certainly see a lot of features like spiral waves, and that's where you can sort of see like it's more dense and it goes out in spiral from the center of the star. So certainly studying them face on at least gives you these sorts of interesting things that you can see that you might not get if it's edge on. Some useful things can be found when you do look at them edge on, though. I mean, you can see ripples that go out from the center near the star outwards, but you certainly don't capture a lot of the interesting spirals and gaps that you get when you look at them face on.
Yeah, it's probably also, it might be easier to measure something like the velocity of stuff going around if you're looking from the edge on, right? Because I think you can quite easily measure the velocity of things that are moving away from you.
Yes.
But it's really hard to measure
Yes.
the velocity of stuff that's moving like along the field of view.
Yeah. So when you look at them face on, you can't. We can really easily tell how fast something is moving towards or away from us. But when all that material is face on, and it's orbiting around its star, then it isn't really moving away or towards us. And yeah, like you say, that's tricky.
Okay. So we got another YouTube question about the gravity of planets. So is the surface gravity? So that's a kind of actually, yeah. Well, surface gravity is the gravity at, well, it's kind of, I think it's actually the force that pulls on a mass that's like on the surface of a planet. Although I'm not sure how that's defined for gaseous planets because, well, there's not really a surface.
Yeah.
Okay, is the surface gravity relative to the size on gaseous planets always lower than that of terrestrial planets? Or are the gaseous planets the ones with strong gravitational fields? Yeah.
Interesting. So I would say, well, what do you think? Doesn't it depend on the density?
I mean, it really depends on how far you're away from the planet, right? So
Yeah.
if you have something, I mean, most planets, or at least the gaseous planets, they get much denser in the center than outside. So the further you go outside, I think less strong the gravity gets. Yeah, makes sense. So there's probably some threshold where the radiation changes. I actually don't know the gravity values like for the gas planets. I know that on, I think, Mars and obviously the Moon, the gravity is much weaker than on Earth, because they're both smaller than the Earth. So in that category, I would say, yeah, bigger planets have stronger gravity. But I think for gaseous planets, it's just, they're so large that it probably counteracts the effect. But I don't know. I didn't look up the numbers, so I can't really say.
It's hard. It's hard with the gaseous planets, isn't it? Because I mean, yeah, you might be on the very edge of the tenuous atmosphere of a gaseous planet and might be fine, but things like when they launched Cassini, when Cassini sort of died, they kind of just sort of launched it into Saturn, and eventually it will get so deep that it just gets torn apart because the gravity is so strong. But yeah, that could be very deep. I don't actually know the numbers for that.
Okay, yeah. Talking about numbers, we got a question. How important are coding skills in astronomy? I think, I mean, obviously, it of course depends on like what you're doing, what kind of particular field you're like working in. But I think almost everywhere you will need some coding skills. So I mean, it's different a lot. So for example, there are fields that do a lot of like really heavy numerical simulations where most of your work will be coding, and there are also fields where you like kind of only do like coding once in a while to kind of, I don't know, visualize some data, make some plot, without like that much requirements. How's it for you, Stephen?
Yeah, I mean, I'm not a heavy simulation person, so I couldn't speak for them. I would say you probably need to know more if you're doing that sort of work. But yeah, I'm just kind of I'm writing code in a way that sort of numerically solves horrible equations, and so most of what I need to know is the maths of that, and then I apply it using code in a sort of logical steps. So, if you go away and try and learn to do some the basics of coding in like Python, then you can sort of use that to solve a problem as long as you apply it logically. But you wouldn't be able to solve maybe a problem I'm doing because it requires horrible maths and things like this. But it's kind of a weird balance. Like I don't go into I'm not sort of weird. I'm not like a super efficient coder who knows every aspect of Python. But I do use code. I have to use codes to solve what I'm doing.
Yeah, also that's a saying, at least in like the computer science people, they often say physicist code, when they refer to like code written by physicists or astronomers, which is apparently distinct in its properties. So you don't have to be a really good coder to work with this things. Like, you're not writing some program that you want to ship to someone. You just want to make some calculations. Another example that I have from kind of my master thesis was basically I spent how like we had to solve some equations of some evolution of of a dark matter particle. In particular, it was called cannibal dark matter. If you want to know more, ask me about it. Anyway, what I did is I spent about a week or a few days kind of solving the math for this and like deriving equations, and then I wrote 3 lines of code, or I wrote 3 lines into a code to solve those equations. So the equation solving part wasn't actually that much coding necessary, but it varies a lot. So these days I'm basically coding every day quite a lot, but I like it. So that's why I kind of chose to go in this direction.
You do spend a lot of your day as well, sort of debugging very small, annoying errors in your code.
Yeah, I think.
Why is this graph that I tried to produce from code sort of reflected in a mirror? Like, why around?
Yeah.
You know?
Why does
you spend a lot of time doing?
Why does my time axis go from today to like a billion years ago, and not the other way around? Oh yeah. Okay, we got a question on how protoplanetary disks form. Yeah, actually, we're both not the experts on this. Do you know a bit about those?
I mean, I have a vague idea, which is basically, you have molecular gas clouds in the galaxy, and something will cause them to start collapsing, and then they collapse more and more and more, and they get hotter and hotter and hotter until fusion starts and you get a star. And then the sort of leftover gases that didn't make that star, that are in the vicinity, essentially condense down into a disk, and that's because they have what's called angular momentum. So when it's a cloud, it's kind of rotating slightly, and to sort of conserve this quantity, angular momentum, when it condenses down into a disk, it then has to start spinning quite rapidly. And that's kind of my idea of how it forms.
Yeah, right. Yeah. And then, as you said before, like, you get these kind of typical rings, because basically everywhere in between the rings you get planets, kind of suck up all the material, and then you're just left with some rings, more or less. Do brown dwarfs also have protoplanetary disks? I would expect they probably have. They should have them like based on the same physical principles as normal stars. There might be some differences. For example, the brown dwarfs don't like have strong radiation, so they. For example, with normal stars, I think the inner planets will always if they are like light elements or gases, they will be pushed out by the solar radiation or by the solar wind, which I guess doesn't happen for brown dwarfs. But otherwise, I think the dynamics should be pretty similar. You probably can't see them because brown dwarfs are quite dim, and you probably don't see like illuminated disks then. But yeah, I would expect them to have them as well.
Yeah, I would agree with that. But I wouldn't bet against it. I mean,
yeah,
this is
okay.
Sort of thing where we would go and look at them and be like, oh, they're not there.
When Andrew's back next time, you can ask him all the details about protoplanetary disks, and also it's really hard to pronounce. And we had questions about Starlink satellites and them affecting research. Did you personally hear something about that? So I heard like a news once in a while, but I'm not working on any observations, so I'm kind of not involved in this. So the Starlink satellites that have you can see them with the eye, or you could see them with your eye quite clearly, like especially shortly after they launched. They were quite bright in the sky. I think there were reports of that they might influence like the work of some surveys, because if they're like in the field of view, they're just really bright. I mean, I don't know the details for that. I think they announced that they want to make them like they want to work on making them less reflective to like make them less annoying for like astronomy experiments.
Yeah, there's still quite a lot to go up yet, I think, isn't it? There's still more to go up, I think.
Yeah, there are a lot of satellites planned. So actually, maybe I should mention this. So Starlink is product, I think, of SpaceX, the company, and I think they want to make some internet infrastructure in space with thousands of smaller satellites. And these satellites had some surfaces that were quite reflective. So when they were at the right position in the sky, they would reflect the sunlight onto the Earth, where you could see them from the ground quite brightly. And they also were quite impressive. They were going in like trains through the sky, so you saw like many satellites behind each other, and it was quite impressive to see. But obviously, if you would like, I don't know, observe some distant galaxy in that direction, such a bright satellite going through your through your window of where you were looking at, it's of course not so good. Right. What is the closest protoplanetary disk to the solar system? Oh, good question. I have no idea.
Yeah, neither do I. I don't.
Are there any like close star-forming
Actually
regions
know that.
that are kind of around, like close to our position in the Milky Way?
Well, yeah, I mean, almost all the protoplanetary disks we see would have to be fairly close, just because otherwise it's really hard to see them if they're actually far away. So I think a lot of the ones that have been observed are actually in our sort of local area. But as to the closest one, I don't know.
Yeah. Okay. I mean, yeah. I guess we can look it up at some point, or you can probably Google it. But yeah, we don't know the names. Can annihilating particles be one particle moving in reality? What about the railroad influencing the electric charge? The forward in time particle and plus the backward in time particle has minus. Okay, I'm trying to understand that question.
Oh.
Yeah, I'm not sure what exactly you are.
Apparently, TW hydrate is the closest protoplanetary disk.
How's it called?
Yes, 170 light years away.
Okay, TW?
TW high. Well, I don't know my life.
Sorry. Okay.
Hydri.
Okay. There you go. Steve, look it up. Okay, I'm still thinking about annihilating particles. Okay, good luck with the remaining part of your homework. So annihilating. Yeah, I'm not sure about the annihilating particle question. So I said there. Okay, so maybe I should mention something. There's this thing called Feynman diagrams. We have kind of a thing that looks slightly like a Feynman diagram here. Well, it's not really one, but it looks kind of similar. So when particle physicists try to compute, okay, what happens if two particles collide? Let's say you have an electron and another electron that collide, that fly toward each other, and I mean you would expect at some point they scatter off each other and that they fly away. And what's the kind of probability that they hit each other, or what's the angle that they will part each other? That's something you can calculate with kind of on the basis of quantum field theory. And what people do is draw these kind of diagrams where lines represent kind of the path of particles, and then somewhere in the center there's interaction, and yet they have two outgoing particles. So in this case, it's about dark matter, but just imagine that these are normal particles. And then these diagrams, there's a special property that you can read them in any direction, and they always are valid. So as long as you construct one diagram according to kind of the rules of physics and the rules of quantum field theory, you can take them in all directions. And basically what you can do is you kind of draw a time arrow, and whatever direction you draw the arrow in, you get a different reaction, but it's all valid. And that's kind of, I suppose, where the idea comes from, that basically a particle going in the one direction could be another particle if the time would be running in the other direction. But that's more like a mathematical kind of principle. Like you could draw this diagram and you could calculate this interaction, and this would be the same result, or you would get the same kind of physics for if you would run time backwards and you switch all the signs of particles. But it's not really something that kind of happens in reality, right? It's not that like two particles are in reality and time is running in different directions for them. It's just kind of the trick that you would use to compute such calculations. Yeah. Okay, so actually I interrupted you, Steve, when you were discussing astronomy experiments.
Oh.
Do you want to go on and present the remaining ones as well? Because I think they were quite interesting.
Yeah. So one that I thought was quite interesting, although I'll try my best to explain it. And so essentially, it's it's investigating how spinning changes the shape of a planet. So what happens is you can imagine if you're going around a roundabout in a car, then as you go around the roundabout, say you're going, well, let me get this wrong because we drive around them a specific way in the UK. So you're going clockwise around a roundabout, and you're sort of turning the steering wheel to the right, and then you feel like you're moving out to the left. And so if you can think about something on the, some material on the surface of the Earth is spinning about its axis, and it's kind of like that roundabout. It kind of wants to move outwards, and that's more so at the equator than at the poles. And so it kind of spinning balls tend to, like planets tend to actually be wider at the equator. They're kind of more like take a sphere or a ball and just sort of squash it slightly, top and bottom,
Mm-hmm.
and it will bulge out in the middle. And so you can kind of see this yourself if you get like a pencil or a stick or something, and then you can have sort of cut out a little cardboard circle, and push it onto the bottom of the stick, and do the same at the top, and then essentially you need strips of cardboard, and then sort of connect them from the top discs to the bottom disc, which are on this stick. It's quite hard to explain. and let the top disc be free and the bottom disc be anchored to the stick or the pencil, and then you can spin it, and you'll see that the more you spin it, the more it flattens top and bottom, and the more it bulges out towards the sides. I should mention that all of these that I'm describing are on a website run by Sky at Night, BBC Sky at Night magazine. So if you want a better explanation than the one I'm doing with diagrams, do go and have a look.
Okay, we can put the link in the description at the end of the video. Otherwise, you can just Google for BBC and Sky at Night, I suppose.
Yep.
Yeah. Okay. Actually, we got a kind of related question about, like, we were just talking about kind of spinning and how the planet forms, or well, how the shapes of the planets, well, how the material on the planet moves. We got asked about why the orbits of planets tend to be ellipses. So, I mean, sure, when you could imagine you have these protoplanetary disks and like everything's kind of moving around the circle, but why does it end up being exactly an ellipse? Yeah, I remember it being like you could calculate it. I'm not sure if there's some intuitive explanation. Do you know?
Yeah, I mean, I tend to think of it as like, a circle isn't a circular orbit isn't different from an ellipse. It's just a very special case.
Yeah.
So an ellipse is well, how elliptical something is quantified by what's called its eccentricity, which is just a number that's between 0 and 1.
Mm-hmm.
And if it's 0, then it's a circle. So that's kind of like a special case. And then the closer it gets to 1, the more and more elliptical it becomes.
Okay.
Yeah, and so it's just kind of it's the case of, if you think about spinning a ball above your head on a piece of string, the ball wants to go in a straight line, but the force of the tension in the string is pulling it back round into this circle.
Yeah.
And then that's kind of what's happening here. The planet just wants to go off in a straight line, but the force of gravity from the star is pulling it around into this circle, essentially. And then with an ellipse, it's just kind of like, sometimes the planet has a higher speed, and it can get away from the star a bit more before the star eventually pulls it back.
Okay.
And then when it pulls it back, it gets faster and faster and faster, but it wants to go in a straight line, so it ends up sort of doing this sort of further from the star, closer to the star, further from the star, closer to the star sort of motion.
So it's basically like you would, like, a perfect circle would be kind of a perfect orbit, and then everything would be fine. But if for some reason the planet gets kind of pulled away a bit from the orbit by, I don't know, something hitting it or another big planet, then it gets kind of moved away from the circle, and then it's a bit too wide, so it kind of accelerates towards the star, and then it's a bit too close, so it accelerates back. And this is just kind of a back and forth, and there's nothing kind of slowing it down, so it just stays in this wobbling around the circle, which is basically an ellipse.
Yeah, and yeah, you're right, absolutely. The things in protoplanetary disks, orbits of material in protoplanetary disks tend to be very circular because of gas, the pressure of gas, and all these other forces, and so things tend to, well, we think, start off very circular once planets are formed and the protoplanetary disk sort of clears away. But then, yeah, the interaction of planets with each other can cause orbits to become more elliptical. It gets very complicated, but it's very interesting.
Yeah.
You should do it.
I mean, also when you look at kind of the solar system, like in a 2-scale diagram, they always look all really, really circular. Like the ellipticity is so small. Like you always say, oh yeah, it's an ellipse, but it's really almost a circle. So it's not that big of an effect, to be honest.
Although Pluto and Mercury aren't too bad.
Oh yeah, quite right.
They're not so bad. They're quite elliptical.
Quite elliptical, where yeah, relatively speaking, indeed they are. Yeah, we got into a new interesting question. When will Breakthrough Starshot fly to Proxima Centauri? First, I have no idea when they will do that, but I think that's a great project, and we can talk about it a bit. Did you hear of that?
Well, I don't actually know what this is.
Oh, okay, that's great. So the idea is, this project is, I think, some quite rich person sponsoring the project, and the goal is to bring a spacecraft to another star. So until now, we only got spacecrafts out into the solar system. So we got some to Jupiter, to Saturn, to Mars, to the Moon, to Venus, all the way to Pluto. But that's like nothing compared to another star, right? I mean, how far is Venus apart? How far is Pluto apart? Like, I don't know, a few tenths of astronomical units. Like stars are light years away from us. Proxima Centauri is, what was it? 1 light year, 4 light years, something like this.
Yeah.
I'm not good with numbers, as you notice. Anyway,
it's definitely order a few light years.
Yeah, there we go, a few light years. So the big problem is when you want to bring a big rocket into space is you have to carry all your fuel. That's a basic problem. So imagine you have a rocket that goes halfway to space. Then you have some amount of fuel. Then you want to break the rocket. Okay, I say I want to bring the rocket all the way to space. So you just put double the fuel in the rocket. But suddenly your rocket is almost twice as heavy. So you need a lot more fuel. So you need to add even more and more fuel. And this gets out of hand really, really quickly. So the further away and the faster you want to go, the much more fuel you have to put in your rocket. So kind of bringing fuel with you is really inefficient if you want to go really far or really fast. And the idea of, in particular, this project, or maybe this is something that was around for quite a long time, but I think through the development of good lasers, it has been kind of remotely become possible. And the idea is, okay, I don't bring the fuel with me. I just bring the spacecraft out in orbit, like away from the Earth with a normal rocket or something. And then I use a laser from Earth to kind of shoot on the sail that's on the rocket. I think it's a laser. I'm not 100% sure, but I think it's like some kind of really directed electromagnetic radiation. So basically a laser or some other, like a maser or something. And the idea is this has like kind of a reflective sail. And just by the energy that you hit it with, like light energy, is enough to propel the spacecraft and slowly accelerate it. And this basically just brings it slowly up to speed, and they want to get it to a really high speed. So the spacecraft is supposed to be incredibly light, just a few grams, I think, or even less, like really light. And the reason is because you just use light to accelerate it, so it has to be really light. And then you can actually get to a sizable fraction of the speed of light and kind of get it on the way to the other star and get there in the order of, I don't know, years or tens of years or hundreds of years, but at least not millions of years. So that's that's already a big step forward.
Okay, interesting. So do they have the accuracy to, well, they're firing this laser at the sail on this very small spaceship.
That's a good question.
How long can they keep that accuracy for? Because you're going to accelerate it to can they keep it for long enough that it accelerates to a good fraction of the speed of light, or will eventually will it be too far away to accurately point the laser at the sail before it reaches that speed?
Yeah, I don't know how accurate you actually can point lasers, but I mentioned like maybe it's kind of similarly accurate to how well we can aim telescopes, and I think we're pretty good at aiming telescopes.
Yeah,
So
that's true.
that might be an indication. Like, I mean, so I think you can aim a telescope. Like, could you aim it to be kind of precisely over Alpha Centauri? How close could you aim a telescope? I think that would kind of work. I mean, you can like certainly kind of aim somewhere on Betelgeuse, which is a really large star. So I suppose Proxima Centauri, like at least roughly, should be possible. And I'm actually not sure if they want to. Yeah, I mean that's one point, and the other part might be kind of steering the spaceship. So I'm not sure if they want to steer it by aiming at a certain part of the spaceship. It would make it a little harder, or if the spaceship itself is supposed to have some kind of steering or some kind of control.
Interesting. Yeah.
Yeah, but it's certainly a really cool project. One big problem is how do you slow down? So actually, that's a really big problem in kind of spaceflight, right? If you want to go somewhere, you not only have to get there, like accelerate to half the speed of light, but also go back down to normal speed again. And actually, the braking is the harder part because, well, it's kind of the more costly part because let's say you choose half your fuel for launching and half your fuel for braking. When you launch, you have to carry all the fuel that you use for braking as well, while the fuel for launching you burn halfway through. So you actually have to carry a lot more fuel with you just to have this kind of reserve left over. So I think in this project they don't plan any way for braking because there's no way to put any fuel on the spacecraft and there's no way to brake by pointing a laser at it. So that doesn't really work. And I think they just want to fly past the solar system and hope they see something nice or get some data. Yeah. Is it possible to use the solar sail in the spacecraft at the present day? So this is it's called the solar. Well, actually, I think it's not called the solar sail in that case, but well, the starshot wouldn't be a solar sail, I think, because solar sail refers to use energy from the sun. And I'm not sure if any spacecraft is using a solar sail, so it would be just a huge piece of, I don't know, like really thin material that you span in the spacecraft and use the solar wind to get carried. I think it's the solar wind. So the solar wind is like particles that get kind of. Actually, I'm not that sure, but do you know more about the solar wind?
So wind, I mean, it's just well, what I understand it to be is a steady stream of particles, yeah, that just ejected from the sun as a process of how it works.
A process of you have a big flaming fireball in the center of your solar system that sends out particles that are quite fast. And yeah, the idea is to have just a huge surface with a really light material, and then you can use this kind of stream of particles as a sail. I think this was like already like tens of years ago. This was a popular idea. And I think it was feasible at some point. I'm not sure if it was actually used in spacecraft yet.
Yeah, I'm not entirely sure. Yeah, if it has been used, but it's certainly a popular thing for future missions. I think that they're looking at trying to make it work.
I mean, it's really a nice thing. Like you don't like it. Also breaks this huge problem of carrying your own fuel because if you use the sun as a fuel, you don't have to carry it. We got a question. What is a solar storm? Do you know about this?
It depends what you mean by solar storm. Are we talking about the effects on Earth of the sun when it's in a its high point of its sunspot cycle? Are we talking about that, or I would understand a solar storm to be kind of like a coronal mass ejection where the sun throws off loads of material and that causes problems.
So is it the same as a solar flare, or are these two different things?
No, I think a solar flare is a smaller version of a coronal mass. A coronal mass ejection will literally eject it right into the path of Earth, and
hopefully not in the path of Earth. I hope that yeah, somewhere in the solar system, I suppose, and it could be the Earth.
Yeah, and then it would travel down the magnetic field lines of Earth, and you'd get a lot of aurora, a lot of northern and southern lights, and it might blow the electricity grid as well.
Oh yeah, fun days.
That wouldn't be fun.
Okay. So how does it happen? Like, is it? I think there's like stuff coming out of the center of the sun, or like out of some inner layers, and like going upwards, and then at some point it's like too fast to be caught, or how does it work?
So I think it's the magnetic field of the sun gets very twisty and it gets caught up in places, and so, for example, sunspots are where it's marginally cooler because I can never remember which way around it is. Either there's more or less magnetic field there, and eventually you can get magnetic reconnection, which is where you have two sort of separate field lines that have a lot of energy in them suddenly connect, and then I think that throws a lot of material out. I think.
Okay. Yeah, I think I heard something similar that's related to magnetic fields. Yeah. Okay, then you get a lot of particles that are flying through space. And yeah, I mean, we're quite lucky that the Earth is protected from these particles. So usually they just go flying through space, but they don't hit Earth directly because we have a magnetic field ourselves. And because these particles are electrically charged, they get kind of guided away around us. And usually they land and impact on the poles, which makes nice lights in the sky, among other things. And yeah, usually they're not a danger. I think there's actually a whole field, like kind of called space weather or something, where they try to predict what the sun is going to do, or will look at the sun and predict what particles are going to arrive here and what effect it will have on communication, on satellites and things like that.
Yeah, so I've just had a look, and it is magnetic reconnection that causes a coronal mass ejection. So yeah, the sort of forced reconnection of the magnetic field lines, they'll just suddenly, they've got a lot of pent-up energy, and then they'll just sort of snap together. And then apparently that releases, I don't quite know how that releases so much stuff, but
yeah, okay. We got actually a question also from not this time but before the last stream on Slido as well, and the question was if there exists anything outside of the universe. Could we burst our universe to get to it? So maybe I should kind of start a bit before that. So our universe is quite large and possibly like infinitely large, probably, but the observable universe is not. So the part of the universe with which we can actually interact is limited by the speed of light. So the universe has only existed for 13.8 billion years approximately. So we cannot see anything where the light would have had to travel more than 13.8 billion years. And this is actually, I think, the furthest thing we can see is the cosmic microwave background. So that's 45 billion light years away. The reason why this is more than the 13.8 billion is because the universe is expanding. So yeah, I mean, I should explain this as well. So the universe is expanding, which means at the beginning it started with kind of a big bang and kind of a big explosion. And since then, ever since, it's expanding out into well, it's just expanding. It's just getting larger. Space itself, space between everything is just getting larger. And this is also why kind of the first thing we can see, the light was emitted, well, shortly after the Big Bang, arrives to us today. So the light traveled 13.8 years and traveled a billion years and traveled 13.8 billion light years. But the thing that where it came from is now 45 billion years away from us. And now the question was kind of, okay, if we suspect or if there might be anything kind of out of our reach and the universe is expanding, could we kind of, well, would there any way for us to affect this expansion, and could we kind of get outside of this? And well, first there's, I think, like at least anywhere near the future, like in the near future, there's no way for humanity to affect the expansion of the universe. Like the universe is just massive and enormous, and there's not really much we can do to affect how it expands. Actually, I think with the physics we currently have, there is not even a theoretical way to do that. But even if there would be, there is not really, like, if there would be something outside of, well, the part of the universe we can reach, if we make it expand faster, we still don't reach that part because that part will expand faster as well. So they're actually, it's kind of a bit depressing, but there are regions of the universe we will never and we can never, like with no means, well, known to us, to our current physics, reach, because they're just really far away from us, and the universe is expanding really fast, and not even with the speed of light you could get there kind of fast enough. Okay, that was an excursion to get off my field, the cosmology and how the universe expands. Back to our solar system. A YouTube question. What's the explanation for the diversity seen in Jovian moons? Should they be more similar if they formed from the same region of the protoplanetary disk? Whew.
Well, yeah, this is interesting. I mean, well, there are different types of Jovian moons. So you have the inner regular moons. So, for example, the most famous are the Galilean moons. That's Io, Ganymede, Callisto, and Europa. And then there are what we call the and there are also what we call irregular moons of Jupiter, which are they orbit much further away than the regular moons, and they look a bit weird. It's kind of clear that they don't come from the same place. And so basically, there's many different ways that these moons could come about. So it's thought that the regular moons would have formed in a circumplanetary disk. So like we had the star forming and then a protoplanetary disk around that in which the planets form. When a planet forms, we could have a circumplanetary disk around which the moons form. The moons form in there. So that's where we think the regular moons come from. And then the irregular moons, which have, orbits that are far away from Jupiter and quite high, inclined to, say, the orbits of Earth around the Sun or Jupiter. These could come from what we call capture, which is essentially back in the day when the solar system had just formed, there was a lot more sort of free-floating small material, like the sort of stuff we see in the asteroid belt now or the Kuiper belt. And this stuff is going to be affected by the gravity of the giant planets like Jupiter and Saturn. And Jupiter could capture these into orbit, and that's where we think those came from. Although they've evolved since under many different processes. And so it's a challenge to figure out, just how much was originally captured and how much was lost over time. And so this is that's sort of two different ways that Jovian moons come about. If you're referring maybe to why does Io look so different from Callisto, or what's the cause of the difference in the regular moons or for even the Galilean moons, like why Io is this big volcano-y hot mess, and it's Europa, isn't it? That's the sort of ice world, is it?
And
And
no idea.
and then I think Ganymede and Callisto are fairly quiet. I don't actually know what the reason, like what is the cause of that diversity. I mean, I know Io is so what we call geologically active. It's got lots of volcanoes and it's spurting up a lot of lava, and that's because of the effect of Jupiter's gravity. What's called the tidal effect from Jupiter. It kind of squashes and squeezes Io, and that that's the cause of that volcanism. But as to why Io undergoes that and the other Galilean moons don't, I'm not entirely sure. It might be to do with their size or their distance from Jupiter. But it's a messy process, moon and planet formation. There's all sorts of stuff that could happen.
These tidal forces are actually quite interesting. Like that's kind of what we discussed in the very beginning, right? We were asked if the gravity of planets is different, like depending on how far you're away. And for example, with Jupiter and the Moon, that you have I think it's because the gravity is different strength at different points of the Moon, right? So the point of the Io that's closest to Jupiter and the point that's further away from Jupiter get pulled differently, with different strengths. So the point that's closest to Jupiter has a stronger gravitational field. So there's a different kind of force on that point. So this kind of pulls apart the Moon, because the force at the center is stronger than the force at the end. And this makes it kind of be volcanic, give it energy and make it a dangerous place to live.
And also, so just to reinforce how differences could come about, things like being more volcanic through the sort of tidal effect of Jupiter. This can come about if you're closer in, and also if you're on an elliptical orbit where you're closer in at one point and further away at another point. Then that can squash you and then unsquash you and then squash you again, which can exacerbate the effect. And so it all depends on all these different things, which is why everything is so varied. Nothing's ever completely the same.
Okay. I heard that our moon did form in a like a collision with or that we suspect that that the moon of Earth was formed in like a collision with another object at some point in the far past. And so did this also kind of create this disk around the planet, or was it more like, oh, just one chunk fell off and now it's a moon?
No, I think well, I mean, it's completely unknown, obviously, but I think the current favorite theory is that Earth had this collision with another planet in the solar system, and then that threw off material into a disk around the Earth, and then the moon formed in that disk, much like how the planets formed in a disk around the sun.
Okay, that's cool.
It's quite neat that you get the same process on smaller scales.
Yeah, that's really nice. If you like, wrote a computer program for the one thing and then you just had to change the numbers.
Yeah.
Yeah, and of course you can also like take a lot of physical understanding. Another YouTube question. If we take all the stars systems in the universe as a sample space, is it more likely that that planet has natural satellites or not? So I mean, I think at least that most of the stars we know, I think as far as we found out, most stars do have planets, or on average a star has a planet. So now the question is, okay, given that they all have planets, how many of those planets do have moons? Do we know? Do we know about this?
I mean, I'm not sure of it. I don't think I know of any confirmed planet around another star that's confirmed to have a moon. There's all these things, all these observations we make that we try and explain, and sometimes, or maybe it has a moon as and could be a nice way to explain what we see, but we're never sure. I don't know of any definite detection of a moon around another planet. But I mean, I would think, given that moons can be quite prevalent in our own solar system, I would say they're probably quite prevalent in other systems. I mean, that's not to say that there always is a moon, because I think Mercury doesn't have any moons, does it, in our solar system?
So. Last time I talked about moons, people call us out in chat. So last time we were like, I don't know, listing moons of some planets, and we missed some. So I'm not going to talk about moons anymore. But I think Mercury doesn't have any moons.
Yes, I'm pretty sure. But what we think happens when planets form is, you have the protoplanetary disk around a star, and then planets form in that disk, and you get a lot of leftover small bodies that didn't go on to form planets. So in our solar system, we see these remnants in the asteroid belt and in the Kuiper belt. But basically, we think, once planet formation has just happened, there's a lot of these bodies floating around, and these are going to be affected by the planets. Some are going to get captured by the planets. So, like I said, that's where the irregular moons of Jupiter might come from. So, if this is what is also happening around other stars, then it's quite likely that these planets will have some moons. As to how common moon formation in a circumplanetary disk is, I don't know, but there's certainly lots of opportunities for planets to capture small bodies that have just been left over from formation.
Okay. Another question we got on YouTube a few minutes ago was, is it possible to find something like a golden plate made by another species? So I think this is referring to this plate that's on the Voyager probes. Actually, I think I have an image of those here. So yeah, when we sent the Voyager probes, that's there we go. Let me move the chat a bit further away. That's a spacecraft, or actually two spacecraft, Voyager 1 and Voyager 2, that we sent out into space that actually have left our solar system like quite a few years ago, and are kind of flying through interstellar space, I suppose now. And they both have, I think both have this kind of disk on it, which kind of contains some information on where our planet is and who we are, and I think there's a picture of humans on there and a bit of information, and I think a guideline how to build a player for this kind of disk to play the information on it. And I think it's supposed to kind of be a message to other species that might find these probes. And the question is, if some other species maybe did the same, how likely are we to find such a probe and capture it? I think finding would be already a really hard part, because I mean this thing is really small. I don't think it's like visible in any particular way. Like it's not it's not sending out any light. And if there's not any star really close by, it won't be like reflecting a lot of light. So if you look out, for example, in the night and you look to the sky, sometimes you can see satellites in the sky. They're quite dim. Actually, the ISS is really nice to see and also quite predictable. If you want to do this one day, I can recommend, like if you have a clear night, you can look up online when the ISS will be over your wherever you live, and you might be able to see it. And the reason you see these satellites or the ISS is because they get the light of the sun gets reflected from them to our Earth, so you can see them, or to your eyes, and you can see them. The problem with the spacecraft somewhere in space is there's no light nearby. I mean, they're just stars really, really far away that would illuminate them. So it's really hard to see. It would need really advanced technology to find them. So do you have an idea how close would such a probe have to be for us to find them?
Well, I mean, they would certainly have had to have aimed it at our solar system for sure. I would say, I don't know. I reckon there might be a half decent chance of finding it if it were fairly close, but I can't be sure. It depends how big it is and how reflective it is.
I mean, they could just send a huge cigar-sized rock, and
yes, that's true.
We might find it. But yeah, I mean, given that like we kind of find asteroids and comets only like when they're kind of close to Earth. I mean, we can't even see all the objects in can we see all the objects in the asteroid belt? Like, I don't think so.
I think there's definitely a size limit.
Yeah. And I mean, they would be quite close, so I think it's really hard to find such objects. I think the next question would be how do you like catch them? I mean, suppose something is coming from a few light years away. It's probably quite fast. I mean, otherwise it would take forever to get here. So how do you catch that without kind of like destroying it completely? So you have to like somehow, I don't know, fly close by and then attach to it and slow down. That's actually quite a complicated maneuver, I think. Yeah, so it's not trivial. I think there was a lot of critique on the idea of, oh, let's send a message to other species. I think it's not really realistic that they will be found like anytime soon by. Well, I mean, the future might, like, I don't know, aliens might have much better technology than we have. At least look at our own kind of history of science and inventing new things. I think in a few thousand years we'll be much further. So who knows? But currently, I think it's really unlikely to find something like this.
Yeah, it's an interesting question there. Yeah.
Okay, and we have a few minutes left. Do you want to give us a final astronomy experiment for at home?
Okay, let me have a look. Well, I mean, these ones are probably not as interesting as the ones I described before, but yeah, I mean, that you can do a sort of simple experiment if you sort of find online. You can kind of get scaled distances between the planets. So obviously the actual distances between the planets are absolutely enormous. Sort of millions of kilometers. But you can kind of say, well, if this one is twice as further away from the sun as this one, and this one is 5 times as further away from the sun as that one, then you can sort of say, well, I'll let 1 million kilometers be a centimeter or something like that, and then you can lay it out yourself on the floor and see, well, okay, well, if Earth is a centimeter away from the sun, then Mars is so many times further away, so it's so many centimeters, and then sort of really get an idea of the distances between the planets, because the inner ones start off being fairly close, but once you get further and further out, like Pluto can just be really far away,
Yeah.
Compared to maybe sort of Uranus or Saturn.
I just remember I had a similar thing. Like when I was a kid, I had like kind of paper planets like on strings on the ceiling. I'm pretty sure they were not to scale. Like the distance was far close for that. I think you could like put them on your ceiling and see if you can fit it in your house.
Maybe I think they also did it for the Open Day last year at the Institute. They have observatory drive, this kind of long long driveway
Right.
at the department, and they have these things that usually just kind of sit on the side by the telescopes,
Yeah.
which kind of give each one has a planet on it and it gives information about it and has a big picture, and they kind of space them out as they would be in real, to scale. And yeah, Pluto was just all the way, all the way at the end of this long driveway, and Mercury, Venus, and Earth, and fairly close together. But yeah, no, so that's kind of interesting.
Yeah, in general, like distances and scales in astronomy are always really fascinating and really, really hard to imagine. Like when you just compare the size of the sun, like it's massive compared to like the Earth, and then you compare the size of the sun to like other like much, much larger stars, or to even like the distances between stars. Like if you see this huge star like compared to the Earth, and you see it's like amazingly huge, and then you compare like the star compared to like you make the distance between two stars, and they're like dots, like they're so small. It's just so amazing. And then you're just to the first star, right? I mean, then you're just within the Milky Way and within like a really tiny part of the Milky Way. And then like you compare like the size of our galaxy compared to how far another galaxy is away. It's also so small. It's like it just gets so large on like astronomy scales. Like when you look at the distance to another galaxy or like galaxy clusters, it just gets like I can't imagine these distances. I gave up on this quite a while ago. But it's really impressive. Yeah. Okay. So we're already at 7 p.m. or 8 p.m. depending on your time zone or whatever other time. That's 1 hour anyway from the start. So thank you all for watching, for all the nice questions. Thank you, Steve, for being here and answering all these questions that I had no idea about.
Yeah, it's lovely to be here.
Yeah, if you want to come and ask more questions, we'll be here next week again. Same time, same place, Monday evening again. You're welcome to join. And there are also other events going on the YouTube channel. So if you are watching on YouTube, or go and check out on YouTube, on the channel, there's, I think, a book club going on very soon. So yeah, check that out. And otherwise, see you next week.